Hey guys, welcome. So may the Lord Christ bless this video, bless you and I, and in fact may he bless this video series. But this will be the first of 8 videos on limits in calculus. As this is example 0, we're going to talk big picture in this example, and then in examples to follow we will see some algebra techniques for dealing with limits. We're going to see a variety of algebra techniques. Each example will be very different from the other. And we'll conclude with example 7, which will be about limits at infinity. Okay. So all the limits that you want in one series of videos, including limits at infinity. Okay, that's example 7. And so how do we start this? Well, so I have several videos on the formal definition of a limit. The precise definition of a limit, which is a delta-epsilon argument. It's a delta-epsilon limit definition. So we cannot really talk about limits without talking about that briefly. Because I have videos dedicated on it, I'm not going to talk about it at length in this video. You can watch those other videos I made a while back. But if this is x and this is y, then let's throw us on this a portion of a function. And let's say that the portion of the function we're looking at looks like this. And let's consider the x value a. And a clearly has a y value somewhere about here. Let's say that this y value is, and this portion of our graph is getting in the way. So this portion of the y value is L. So I'm going to keep our graph short up to there. Fair, not crowding my drawing. Okay. So the formal definition goes like this. We'd say that the limit, we'd say in this case that the limit, if we call our function f, is x goes to a. This is how you read this. Lim is x goes to a. The limit is x goes to a of the function f of x. We'd say is equal to L here. And here we could just see and tell, right? Okay. But the formal definition is that the limit is x goes to a of f of x is equal to L if for every epsilon greater than 0 there exists a delta greater than 0 such that whenever 0 is less than the absolute value of x minus a is less than delta, it automatically follows that the absolute value of f of x minus L is less than epsilon. What? Okay. I explained that sufficiently in the other videos that are dedicated to the delta-epsilon limit definition. But as I said, we need to mention it here at the start, and so let's do that. Let's decode it. So again, I've decoded it sufficiently in those other videos. It's not as hard as it looks. All it's saying is this: it's an epsilon challenge. So you set an epsilon. So you say epsilon is this number, and let's say that epsilon is this distance here, right? This distance from L is epsilon. So you've given me an epsilon challenge, and this part here, the absolute value of f of x minus L is less than epsilon. All it's saying is that the distance between L and f of x is less than epsilon, right? So you set your epsilon, and because this is an absolute value statement, we have to consider not just L plus epsilon, but also L minus epsilon. So now we have an epsilon neighborhood about L. So you specify some epsilon, and we create an epsilon neighborhood about L, and this is a challenge you give me. If the limit is in fact L, that is the limit value is in fact L, then what I must do is come up with a delta greater than 0 so that if x minus a is less than delta, meaning I am considering an interval about a that goes from a minus delta to a plus delta. So he gave me the epsilon, and my task is to find a delta so that whenever I am in a delta neighborhood about a, all x values in this delta neighborhood about A are mapped into this neighborhood about L, this epsilon neighborhood about L, to be specific. So again, what you're doing is you give me some number epsilon, as small as you want, and then we go L plus epsilon, L minus epsilon, and create an epsilon neighborhood about L. And my task is to find a delta so that all x values that are in a delta neighborhood about A are mapped into the epsilon neighborhood about L. If you could do that regardless of the epsilon, then in fact the limit is x goes to A of f is L. Meaning if I keep shrinking this interval about L to be as small as I want, and then I could keep shrinking this interval about A as small as I want, so that all the numbers in this small interval go to all the numbers in this small interval, and I could do that regardless of how small epsilon is, then this statement is true. Yeah? Okay, so that's the precise definition of a limit. But we don't need all that jazz if you're just trying to do some first set of homeworks on limits. You'll need perhaps to understand the concept better, so I'll dedicate a little bit more time explaining the concept, and then you'll see the actual practice at the end of this video, but also in examples to come, examples 1 through 7 to be precise. Yeah? Okay. So where to now? Well, so then we see that it probably goes without saying, but that, like, you know, linear functions are have limits everywhere, right? They have limits everywhere. For every x value of x is A, I move it there, doesn't matter. The limit exists for linear functions, right? And same is true if we have quadratics. Same is true if we have cubics. Or the fancier functions like sine and cosine, or even e to the x, the natural log. All these guys have limits everywhere. Everywhere in their domain they have limits, yeah? And for most of these guys, their domain is all real numbers, so they have limits at all x values, yeah? So what kind of things don't have limits? These kind of things. Let's consider this here. Consider, that's higher up than I want, but it's okay, we'll live. Yeah, consider that, and then what do I want to do? Then this. But I can't have that, sorry guys. It's caught in two minds. Okay. So let's say that this is the function f, and f is f of x, right? We can define piecewise. Let's do it here. F of x is equal to, I can define it piecewise as being, well, to the left of 0, we have a parabola. So let's say x squared plus 2, x is less or equal to 0, right? And then we have a line to the right of 0. What slope does that look like? Doesn't quite look like 1, so I'm going to go with 5 over 6x, and then say that's plus 7 over 6 now, whatever, I'll keep it simple, plus 1. X is greater than 0, right? Okay, now because we said that quadratics have limits everywhere, this quadratic has limits everywhere it's defined, and so in this case it has limits everywhere where x is less or equal to 0. And we also said that lines have limits everywhere, so this line has limits everywhere, and therefore it has limits everywhere when x is greater than 0. So the only place we're concerned about f not having a limit is where this jump happens, which is at x equals 0, right? And so here we will say conclusively that the limit as x goes to 0 of this function f, right, this function right here, f of x, does not exist. And that's because if we get close to 0, x equals 0, if we get close to it from the left, so, you know, approaching it by picking numbers like negative 0.00009 and then getting closer and closer. But as we approach f from the left towards 0, as x goes to 0, from the left, the y values are getting closer and closer to whatever y value this is. And let's say it's 2, right? And so then this can't be x squared. Well, yes, it can be, duh. Sorry, guys, sorry. Yes. So if this is 2, if that y value is 2, as I get to 0 from the left, clearly I'm approaching the y value 2. Whereas as I get close to 0 from the right, like so picking numbers like 0.0001, but positive numbers, getting closer and closer to 0, then y values are approaching this here, and let's say that this is 1. Yeah? So we can summarize that by saying this, which is the limit, there is one-sided limit, and here we encounter it. Limit is x goes to 0 from the left. This is how we'd say x going to 0 from the left, meaning approaching 0 from this direction, coming from the left towards 0, right? And as x goes to 0 from the left of f of x, we said we get 2. But the limit is x goes to 0, as x goes to 0 from the right of f of x, right? We said as x goes to 0 from the right, the y values are approaching 1. So this is equal to 1. Well, that means that the limit from the left is not the same as the limit from the right. And I've never cared to watch this movie, Mean Girls, because I'm a guy and not mean. But yeah, in it, some girl, like in a math contest, says, the limit does not exist. That's my students telling me, like I've never watched it and I never will. Okay, but yeah, there's such a thing as one-sided limit from the left and limit from the right. So that's important to pay attention to. And as you can see, it's easy enough if you have the visual how to tell what the limit from the right and limit from the left are, and whether or not the function has a limit at a specific point. Clearly, if your function has a jump discontinuity, that's what this is called, jump discontinuity. Okay, don't test whether or not I can spell discontinuity. I can. I'll do it later. But yeah, if your function has a jump discontinuity at a particular x value, then the limit at that x value does not exist. Yeah? Okay, so we summarized this in this way. Let's pick up the pace. I feel like kind of being sluggish a little. Okay. And so what's the next idea? Well, the next idea is, how about in this situation? Let's consider this. So let's consider f of x is equal to x plus 2. Yeah? Okay, now what does this look like? Yes, this is important to start here, even though it looks simple. X plus 2 would be like the function with slope 1 and y-intercept 2, right? So this is y equals x plus 2. Okay, now I create a function g of x, and I go g of x is x squared minus 4 over x minus 2. Clearly g of x, right, is equal to x plus 2 times x minus 2 over x minus 2. And so all I have done to create g from f is I wrote f of x as being like over 1, right? And then I multiplied top and bottom by x minus 2. That's all I've done. And so I multiplied by 1. I multiplied f by 1 to get g. And so how are they the same? They should be the same. Well, in fact, they are the same everywhere except for x equals 2. So if I were to graph g of x instead of f of x, notice I have a graph of f of x. If I were to graph g of x instead, this is all I would have to do. I would have to say this is now g of x, which I won't rewrite, but g of x is this, right? Clearly, x squared minus 4 over x minus 2. And the only difference between g and f is at x equals 2 here, if this is x equals 2, g has a whole meaning that y value is not defined, that is not visible to you. So how about this? How about a giant? Oh, okay. So you'll remember it now. Okay. So at x equals 2, G has a hole, but F doesn't. That's the only difference between F and G. Okay. So does G have a limit as x goes to 2? Well, let me ask you this. Does F have a limit as x goes to 2? Yes. Right? The limit is x goes to 2. And I don't need this portion here. The limit is x goes to 2 of f of x is equal to 2. And I could just plug it in. I go limit is x goes to 2 of f means limit is x goes to 2 of x plus 2. And I plug in 2 and I get 2 plus 2, which is 4. So, but I'm not considering limit as x goes to 2. I'm considering limit as x goes to 0. My bad, y'all. But in fact, the limit as x goes to 2 of f is 4. But as I wrote here, it's correct. The limit is x goes to 0 of f is as x goes to 0 of f is 2. My bad, y'all. But what I want is the limit as x goes to 2 of f, which is 4. My bad. Okay. So it's 4 here, but the limit is x goes to 2 of g is what we care about, and g is visualized there, right? Okay. So limit is x goes to 2 of g. Limit is x goes to 2 of g of x would be limit is x goes to 2 of this, but wait, I can't plug in 2 into there. Yeah, so the first example will teach you the first technique, the algebraic technique that you need to get around limits that are like this, yeah? But because we know what g looks like, we could just go and look, right? And so because we know g is this here, this line, except for a hole directly above x equals 2, an exaggerated hole at that, what happens as we pick points closer and closer to x equals 2 from either side? Well, the y values will approach this value, whatever this value is, right? But wait, before we put the hole there, we know that that value is 4, right? Because f would have been this without a hole, right? And so the limit is x goes to 2 of g is 4. I won't say how you could do that. You'll have to wait until example 1 to see how we deal with limits like this. I'll provide you 2 examples in example 1, and in fact I'll do that in each example. But yeah, having knowledge of what g looks like, you could just see that as we get closer and closer to x equals 2 from either direction, left and right, we get closer and closer to this y value, which is 4, right? Okay, so this is called a removable discontinuity. And here you go with your discontinuity. Discontinuity. Yeah? Okay. So removable discontinuities, limits exist at places where you have removable discontinuities. Jump discontinuities, no good. Don't jump. Don't listen to Chris. Okay, don't jump. All right. So it's next. What is next? Well, I think, we've said, oh, that's important. And as I said, most of the functions that you deal with have limits, right? And so, because I'm not going to dedicate an example 1 to these couple of examples I'll show you here, let me show you the couple of examples. So in practice, this is what you do. Like if you had x squared, let's say plus 2x minus 3, and you're trying to find the limit as x goes to 2, you don't need to graph it. You don't need to do anything fancy and see the left limit and right limit. It's a quadratic, it's a polynomial, it has limits everywhere, and what you do in practice is plug in 2 for x, not plug in numbers that are sufficiently close to 2 from either side. You don't need to do that. Yeah? Okay, so this here in practice would be like 2 squared plus 4 2 times 2, minus 3, which would be like 5, right? Okay, cool. So that's that. And no problem if you have a fancier function and say you're trying to do limits x goes to e of the natural log of x cubed. This is just the plug it in if you can. So we can. And this would be 3 ln of e, and therefore 3, right? Okay? And don't assume that just because you have a rational function that you cannot evaluate the limit. Here's an example. So suppose you're doing this. Right? Well, if you plug in 2, nothing bad happens. You get 0 over -1, which is 0. So even on rational functions, if you can plug it in, just plug it in. Yeah? Okay, cool. All right, that's it for example 1. I don't think I left out anything important that I wanted to say. Yeah, and left-handed and right-handed limits, if you have the functions graph, are easy enough. Otherwise, I'm sure we'll encounter one of them in the examples to come, so we'll check them out. Keep watching. Take care.